Weekend. Okay, it looks like it is successfully recording. Okay, so last time when we left off, we had talked a lot about electron shells and how we get from basically individual shells to bands, get some idea about the energy gap. We mentioned the Finity energy, which is kind of takes the energy of the available system values of thermal and stuff like that. So it's somewhere between conduction and valence, right? Conduction on top of right? And since it's kind of between there, it's the free energy that's available. And you can't have partial, right? There can't be something in an energy state in between. So it's either all the way down or all the way up. I think that Fermi energy can be thought of as like the net average between those ones. So it's thus also the probability that anyone will either be found at the top or the bottom. So it kind of gives you a nice relation to that probability and stats area, right, where we can kind of talk about which level is it at. So if the Fermi energy is lower, then less likely to have an electron in the conduction band. If higher, you're more likely to have it. Right? So that's yay kind of stuff we like. All right. Now, we mentioned this is true for what we call intrinsic semiconductors. Ever heard of that one before? Yeah, and then goes in. So what is an intrinsic semiconductor? Yeah, and then goes in. It's not. Yeah, this is just kind of where. So like silicon is an intrinsic semiconductor. Right? Basically, column 4. These are ones, they're kind of halfway when they form their lattices. They've got that chance. The gap is small between valence to conduction that there's a reasonable chance you're going to have. Now, that's lovely, but it's still, there's not a. And here's one of those kind of issues. So let's imagine I have overall a silicon lattice. I guess we're going to get some red here at the moment because that's the pentagram. So imagine I have a lattice of silicon. And they've got, if you look at their outer shell, they've got 4 electrons. So they're going to form bonds like this because this allows them to pair up with their neighbors. All right, they kind of share electrons between them. And once they've done enough of these all the way around, right, they're going to effectively have 8 in the outer shell. So they're going to think they've got a complete shell. That's awesome. That's what they want. These are what we call covalent bonds because they're sharing them pretty equally here. What we were talking about last time actually shows why covalent bonds work. This is one of those kind of cool things, the explaining power of quantum. Remember we talked about how the individual bands, when they come together, they get close enough, they'll kind of split, right? Because you still have to have 4 positions, the up, down for each one. So one goes down, one goes up. Well, the covalent bond goes into that low shell area, right, in the band. So that means essentially it's dropped to a lower energy, and the bond has a lower energy than the free state of separated. Nature likes to go to lower energy states, so that means that bond is stable. If it didn't do that, it would actually effectively, you'd lose a couple of the positions. Neutrons would have to move up to the higher shell energy. So it'd be really hard to make a bond in the first place. And they get a lot of energy back if they split apart. So things like O2, which is a covalent bond, would not like that state, and it would push apart. So oxygen would be exploding. And it would not be very conducive. So we know in some sense when they come together, it's kind of a energy state, and that splitting shows us how you get. So that actually shows you what the covalent is stable too, which is a side benefit. That's partially why I spent the time I did on quantum. as engineers, you just ought to understand some stuff. People ask you weird questions, and it will come up at times. Why does this happen? What's going on with this? If you know it, you're able to explain it. And that's part of the power of this stuff. All right, so we've got these all shared. There's a whole giant, you know, actually, if I had my druthers, I'd draw 9 of these. So I had one that was fully formed, but I'll probably stop at this point because it gets kind of annoying drawing all these. But you get the idea of these matrices. They're actually, the electrons are flat like this. 2 are slightly up and 2 are slightly down. So it kind of forms this rough shape to it. It's like a tetrahedral diamond. If you've ever seen, make a bunch of tetrahedrons in space together in space, that's essentially what it's doing. So you kind of get this shaped, some half up, half down type of area. But from the top, it looks pretty flat. Now, some of these will occasionally pop out. And when they pop out, maybe I should use a different color. What's this one? Looks like blue. So one of these pops out and ends up in the conduction band, which I'm just going to draw here. That leaves behind a hole. Now, they're close enough together at this moment that we can say essentially the positive from the your core, right, your nucleus, cancels out that electron in the greater scheme, and it's electrically neutral. But since it's easy to move about, this one can just kind of wander all through it, which is where we'll get direct currents and things of that sort. Right? Or if I impose a field, even a small amount of energy when it's free, right, an electron is so small it's going to it's going to be moving in blitz and things. But then behind is a net positive charge. So that's coming from the nucleus. But for all intents and purposes, it looks like I see a hole in the lattice, and now there's a positive charge. So it looks like nothing has a positive charge. So we usually say the hole has a positive charge. This is a convenient fiction. Holes do not have positive charges. But it's a lot easier than explaining the whole thing. Yeah, right. Essentially, but something else might be wrong. Now, these are going to be our 2 carriers, right? We're going to have the hole, right, which will be a carrier, and we're going to have the electron. Because some other electron, let me pick a different color. Let's see, it'll be black. Let's say this one decides to pop up, and it moves over and it falls in the hole. Right? It's going to look like that hole. I'm not saying the hole did move. I'm saying it looks like the hole because nearby it will up and then into the hole. So the net effect you see is you see the hole changed its location because everything else looks. And you can't keep track which electron was where. You just see electron shuffle and this little positive charge movement. So really, for a hole to move, it takes a near electron pump up, move, fall in. How much work is that compared to an electron movement, which needs the electron to move out of this distance? There's two. It takes up, over, down, or if you like this up and down. This is actually placed. Holes move a little bit slower than electrons do. There's more energy for it. So when you look at the speed of holes, technically, holes are worse than electrons. They just don't use not quite as good. But if you really get into semiconductors and doping and that, we're not going to sweat it here too much, but you should know that basically electrons are a little bit better working than holes, because holes take an aggregation of simple electron moves. Electron move just takes the electron. Does that make sense? Okay. So this gives you kind of that intuitive feel. So now we, yeah. You actually don't see them. We never watch them. What you're actually seeing is you're going to see the overall one action. I mean, you could come in and do some type of heavy, watching, you get some electron microscope or something. You might be able to watch this, but we don't care. Right? So physicists will care. We don't. Right? Because you're going to have tons and tons. Like I do a little bit of this. You're going to have a big chunk of semiconductor material, relatively speaking, which is going to have tons and tons of these. Until you get down to single atom transistors and stuff like that, you don't necessarily have to worry about those effects. We're considering kind of more bulk effects. Now that means if you see any current or anything flowing, it's the net effect of a lot of these actions. Now, a lot of these actions are going to be built up. So, like, we do notice that overall, things flow slower in a majority P-type whole carriers. Those materials flow a little bit slower. Their net currents are not quite as good as an equivalent amount of electrons. Right? So why? Well, it's kind of a build-up of a whole bunch of smaller ones. But we don't really care about the individual actions beyond just the explanation of the voltage. That makes sense? Yes. It's just thinking of like, if imagine you're watching a crowd of people. We can explain like crowds kind of when you get a lot of people, it starts slowing things down by looking at individual interactions. But if you had to monitor how a crowd was working by monitoring each person, that's a heck of a lot, as opposed to just putting something that cuts people to the side. And you could think, oh, certain structures work better to let people go through. And we're engineers and we care about the structures that go through. So it is legitimate to look at individual interactions, and as you start getting to smaller structures, it's helpful to look at. So if you work with my Derek Lane, who cares about single atoms, you start batteries, right? I care about more bulk materials because that's where most of my work is. So I don't care. And that's generally for most of our areas when we're building them. We don't want to build something that's small because bigger structures also tend to be more immune to radiation and they tend to handle static discharges better, stuff like this. So if you make something really, really high need, it's more potential. And the two interest areas have to just radiation and space, which is radiation. So both of my things. And so generally speaking, and a lot when you get into just the general digital side of it, we have to deal with areas where things get really challenging. They're in unpleasant environments, all kinds of stuff. So again, we're dealing with that. So unless you're in a very controlled environment and you're looking for speed and some days of heat, which is part of the game, but that's a specialized area at this point. You're kind of stuck in individual things. So I get that would be the best way to just talk to you. Don't overthink it at this point. Look at the aggregation. And from that, you can then step in and say, okay, I know what was happening. Good questions. Okay, so we feel comfy with this. Yes. So wouldn't it be nice if I could somehow boost the number of one charge carrier or the other? Be kind of helpful thing, right? Well, what if I took one of these and inside my silicon, I'm going to have to draw a couple more at least to kind of add this effect. I add some new element. I'm just going to call it X at the moment because I don't want to keep having to draw multiple of these. All right, and we're going to have X. Let's say, for instance, we make X pentavalent. All right. Anybody know what pentavalent is? Five, yeah. So I've got five in the outer shell as opposed to silicon, which is four. So for instance, this could be like X could be, say, phosphorus. right? It's pentavalent. So it's got that, and it's got one more. Now, when this happens, phosphor is a shell, right? It's got more nucleons, so those more positive charges, it's going to pull the shells in. So each of those shells will draw, but it's got one extra electron. So relative to our silicon, it's got something that would look like it's in the shells. Does that make sense? So if you think of it in terms of the original silicon, we had kind of, um, here's my conduction band, and here's my valence band. Now, it has slightly lower energies, but it's got one that's up above the four, right? So this is that fourth electron's energy. Well, it's got this fifth one, but it's pulled in a little tighter. So it's close to the conduction band. Right? Its energy shell, but it's a little tighter, so its energy is a little bit lower. But it's adding one electron, and it's close to the conduction band. So it gives me one kind of readily available near that conduction band. It's above wherever your tape electron is. So in essence, it's kind of got some Fermi energy here. So think how easy it will be for it to come up. It's, yeah, crazy easy. So now you're going to, as we put a whole bunch of these in here, right? I'm, we call these, since this adds electrons, right? We're going to call this a donor. And so this is, in particular, ED, right? The energy of the donor. The Fermi energy is a little bit so it basically allows me to easily get some electrons that can move. So now I'm going to have a lot more electrons than holes. Because commensurately, since the Fermi energy moved up to here, right, this one's going here, but for other ones, it's not going to quite be so easy to be able to get there, right? Because this one's taking that energy, the other one's much more likely to be low. So, yeah, it's kind of all over it for them. So, the ability to get some hold is pretty low. So that means you're going to need a lot of electrons and a little bit of hold. So overall, your charge carrier is going to be N. But does this make the material? No, because I've got an extra proton which balances it. So this is electrically neutral, but you just have what we call a majority charge carrier, which is an electron. So your charge carrying is electron, but it's still electrically neutral. This one I sometimes hear people say wrong. So it's important to get there. We get a majority carrier, which is the electron. Good? So now we've got electrons that can move around. We're going to call this, since electrons are negative, we're going to call this an N-type extrinsic semiconductor. It's extrinsic because we have now doped. Doping means to add something in. We have doped in a material that gave us an extra electron. So let me ask you a question. If pentavalent five electrons is good, wouldn't 6 electrons in the outer shell be even better?
It to a point that there are too many electrons in one spaces.
Oh, but more electrons. Electrons are carrying the charge. Isn't that awesome? From that standpoint, it sounds pretty good, doesn't it? There's got to be a problem.
Yeah.
And it does cut off. So the question is, you're absolutely right. The question is why?
It cuts off because you have too many buttons to attack that you can.
So think of it actually think which side are when you look at the periodic table of elements. Here, it's not recorded. Fine. Here's your. I'm not going to draw this perfectly. I'm just going to.
Semiconductors, we talk into
Right. So where are the metals? Yeah, they're over here. Right. And the non-metals, which insulate and stuff, are where?
uh,
So over here, and the semis are boom. Right. So as I go to pentavalent, I'm moving to this side.
yes, there's
Now, so if you think about this, if I start going more and more, in some sense, you're going to expect it to behave like an insulator. But why?
thinking
You are, right? Which has a full shell. But here's the fun. Think about what's happening. When I go to the right, I'm adding extra electrons in the outer shell. But what am I adding? More protons. What happens when I add more protons? Okay. So what's going to happen with those extra electrons? Let me. Which color have I used? Green. No, no, okay. Okay, blue. All right. If I do that, that's going to pull the shell down here. If I was doing like six, right? I had the. So yeah, sorry. Right. So if I did, I have to. It's going to pull it tighter. So what's the gap I'm going to jump at?
the gap between the which
So I'm going to get so it's not where you're putting more electrons, but you're actually making a bigger jump, which I think is great. So you don't want to do that. So that's part of the reason why we're in the energy bands, because it can answer some of the questions. Now you might, by finding the atom that's in that thing, you might find where the energy is in too bad of a jump, and maybe it's close enough. If possible, if not frequent, right? You don't do it as a general thing. Somebody's doing something crazy and they're making some or something. They might find something when that gap isn't too bad. But you gotta make that energy gap. What happens in general, the further to the right you go, the more you're pulling it towards the center, which the worse the energy gap is. If you happen to find something lucky that's the right size, doesn't screw that, yay, good for you. I think you've made a cool advance. There are some cases we want this type of a weird thing because a bigger gap means more energy. Right? So one of the things that goes in order to get energy, you can either use that thermal energy. Is there anything else that can give us energy to cause an electron to change its level? Okay, so I need some type of radiation. What's the most common radiation? Okay, that's a precise. Right? So photodiodes and LEDs, this is how they work. That band gap, right? An electron moves up, it absorbs the photon, it moves down, it emits a photon. There is no semiconductor that doesn't work by, at some point, either absorbing or emitting photons. So it's not like there are some LEDs out there. Everyone is an LED. Right? If it's a PN junction, you're emitting and absorbing light. It depends on the frequency. Yeah. Most of them are not in the visible range. So if you want to, now think about different colors. What do colors correspond to? Frequency. So as you go to higher frequencies, what does that mean color? Yeah, purple blues. So you might want a slightly bigger gap if you want blues or purples, for instance. So depending on if you're trying to shape the color, and what matters to you is the color, which it does with LED, now all of a sudden you care about something. You want a bigger gap there. You're not concerned with how much is flowing. You need a particular frequency, so you need a distance between the gaps. Right? Now you see why it takes some time to kind of develop those particular colors. You got to find the materials to do it. So it's a huge materials. You need them to have these gaps, and it's got to be manufacturable in reasonable ways. So there's all these considerations. Not our biggest concern, but it doesn't touch the end. So just be aware of it. That's also where you always have to put cases and other protections between transistors, because those photons will go out and hit nearby. And if they're all made of the same stuff, you have now made what's called an optocoupler. And it will literally send photons across, which will activate nearby photons. Sometimes we want that property, so we actually make light conductions. Other times we don't, so we have to put something that's an absorptive barrier between them to prevent the light coupling. But if you actually go in and get a transistor and you grind off that little black outer casing that's on there, a number of them will give you some pretty light shows that are activating. Yeah, you can have fun with that one if you want. Do little home projects with them. But anyway, that's definitely getting beyond our thing. We feel comfy with this? So now we've got some type of an N material. It's going to be majority charge carrier electrons, and things are able to move out. You think this is going to be fairly quick? Forward. Yeah. Some of the pulse, yes. Yeah. Electrons, good. Right? You like electrons. Electrons are fast, right? They're already basically right there, so any energies, those things. Yay, we're happy. Okay, what if for X, instead of phosphor, what if I replaced it with, let's say, boron? Right? A trivalent. It's lower. And you're right. So now the shell, when it comes with a new, so it takes, you think, I'm missing one. So I also removed a, I removed an electron from my valence area, right? Because the fraction of the have holes. So this is electrically neutral. Yeah. But it moves. So this hole is on the very top. It's probably like right about here. Just a little bit. Now this hole is close to the other valence electrons, but it won't let you go very far. Well, now, since there's a hole there, that means your Fermi energy gets way down here for Fermi, right? It's going to get sucked in because that's between your last electron and your next. So how likely are you going to get free electron floating about in conduction? Yeah, it's really low spinning. But can you get something to put into that nearby boron empty outer shell, and maybe it looks like valence? It's a little bit of energy, but it's a thing that can jump to, but you can't fly. I mean, it's a one-time jump. So it looks like the whole move. But it's got place in here. So you got one of these that can move. So your rigidity carrier is now a hole. You have a and somebody will jump, but they can't do much at all. You gotta be able to jump to another boron atom somewhere nearby. This is gonna be a very tough maneuver, so it's gonna be slow. But we can get the holes. Now those holes, in essence, the electron moves over. The hole becomes negative, but so and the silicon became positive, but the electricity neutral. But it looks like the hole went into the silicon and created a plus. So it looks like the plus as well, even though we didn't get the electron. So we just talked about this. The best way we can explain of this goes twofold. Now, number one, if you were to use bubbles inside of water, that kind of rise up and move, the bubbles are moving up, but what's really happening is the water is flowing below it and pushing the bubble up. So, but it's really hard to watch the water moving around the bubble. The bubble is the thing that's kind of more unique in the structure. So it's easier to watch the bubble than the hole. The bubble is the hole. What's really happening is the water's flowing, that's the electrons moving. But the missing space rising up is what it is. That's one way to think of it as an analogy.
Yeah, man. Having slower is, yeah,
So just by itself, you'd be like, eh, this is useless. Right? Well, what's the magic is going to happen once we stick the P next to the end. Okay. So on its own, you're totally right. It doesn't make sense. It's in the combination that it will gain its benefit. Um, the other thing that I just mentioned on this is you can think of it in general as electrical engineers. What is the flow of current we usually talk about?
we usually talk about like, things like,
Yes. So there's reality, which is the electron flow, which is negative flowing towards positive areas. But we always talk about conventional current. And pretty much everything is developed on conventional current, which is the flow of positives. But positives are in the nucleus, or holes, if you want to think of them that way, right? And that's just it. So why do we talk about them if they're completely
like, it-
for what? But it's not. I mean, if I had just originally defined everything by electrons, it would totally be right. It wouldn't be confusing, and we wouldn't have to have this silly discussion.
I mean, it's also really strange because we have polarities, which is positive.
Yeah, that's no problem. So you are more as electrical engineers. If you ever get a time machine, I don't care what else you do, your first stop is to go back to Benjamin Franklin and slap it and say the electrons move, the negative charge moves, not the positive. Because Ben Franklin, he has positives and he has negatives, and he's like, it's a very smart guy, right? I mean, he did a lot of amazing stuff, one of which was electricity and all this kind of great stuff, right? But he picked the positives. So ever since, everybody has used positives because it was convention until 100 years later when we discovered it was actually the minuses that moved it. It was too entrenched. I mean, I'll stop with the doctrine. So we have to explain everything backwards. So if you get a time machine, please fix this so none of us have to deal with this again. We can just do it, right? But that's actually where it comes from. This is the other reason it's to be called the positive ones moving because it fits the conventional current flow. So when we get to larger circuit theory, in all, I mean, even though you know it's wrong, everybody talks about it as positive flow. So that's the other way to think about it.
P, which one's N on the.
P is positive. Positives are holes because it's not the electron. N is negative, right? And that's an electron. So you're just, when you're using the P or N, it's talking about the charge of the carrier. Right? What is the majority carrier in the material? It is not the net electrical balance. The net electrical balance is neutral in all of them. It has to be neutral. The ridiculous, calculate sometimes the ridiculous amount of energy necessary to make some area devoid of electrons. It would just be impossible, right? You get even small amounts, and you get lightning bolts and stuff, right? So it's just, yeah, wouldn't be a practical situation. Okay, we're good with P's and N's now, right? So if I do boron, I get positive or holes. And if I do like phosphor or something that's that, I get electrons, right? Which is negative. Um, So you get one of those two as your majority carrier. You will get a few minor carriers, the minority carriers, and I'll show you where that plays in the diode. There is a spot where minority carriers become dominant. All right, now let's take a P and an N and we stick them next to each other. Okay? So all over this N, we've got a whole bunch of minuses, right? Electrons. It's overall neutral, but I'm just showing that carriers. And all over this, I got a bunch of holes. Now, put these two materials next to each other. When you look at the energy band, right, remember the P-type material, a little bit less charge in the nucleus, so their energy levels are up a little bit in that. So you get, right, the Fermis are where they all balance. So you've got, for the P-type material, you've got your valence band here and your conduction band is way above it. And the reverse, so this is conduction, right? Conduction, valence, this is P materials, this is N materials, and we got basically at the so this is the general flow. So you kind of see there's this region between them that goes, but there's some overlap. There always is, right, when they come together. You see some overlap. Now, some of the charge carriers from here can flow over here and then fall in and fill these holes. Right? Now, as it comes back, those ones filling up, going to create a little bit of energy buffer, raise things up. So as they start, these start moving over and filling these holes because it's a little bit cheaper for them. There really does become a true positive over on this side, right? Because that electron is balancing the nucleus. So I get that positive, and this side now has its holes filled, but it's filled by electrons. So it is truly a net negative. Plus, the holes are filled and the electrons are missing from that region. So you get this little region here that's a depletion region. Depletion meaning it's missing something, it's depleted of its charge carriers. The N region has lost its electrons. The P region has its holes filled. And the charge differential has now created almost like its own little battery. You've got pluses and minuses, but they're being held apart by this kind of energy thing. So the energy goes until there's no more energy incentive to do this. But then you just have a pure energy held between them. So nothing can flow. Make sense? So here's the challenge there, right? Now in the depletion region, nothing can flow. I think it can create a little region. It's actually very thin, and it fills really, really fast. And so you stick those materials together, and you have just created an insulator. Right? Right? There's nothing to hold the charges, right? They're in their lowest states. There's a big jump to get out of that state. They're stuck. So you have created an area where nothing can flow. That is a diode. This is why a diode can block stuff. Because innately it blocks stuff. Because the second you stick them together, within a tiny, tiny instant, depletion area forms, and you have a little voltage that causes by that charge. So far, so good? Okay. So you see these all these minuses jump from here to here. So you have the minus on this, and you have the positive. So it looks like the minus plus. So you got a voltage differential here. If you look at this whole depletion region, where it's being moved, it's right, all the bubbles are stuck in the hole. So they can't in essence go anywhere. So there's no charge carriers. Okay? So you got to look effectively like a battery, right? A voltage differential, and you got vision with the charge carrier, so it's an insulator. So no charge is flowing, but you can kind of, there's no net charge, but there's kind of effectively a voltage differential in a local region. That's the depletion region, and that's why nothing flows. Because there's nothing to carry. Right? And it's just big enough that no electron can easily jump in it. If it could, and it would be the depletion region. So no matter how big that region is, the material is much bigger than that. It's gonna grow until there's nothing to happen. Okay? And then you're stuck. So first we're good? So now down to material, let's shoot that kind of stability. Let's now consider with this PN junction here, what happens if, right, so I'm gonna slightly, it's kind of messy here. My P, my N, there's the barrier, and I've got my depletion region. We said there's a bunch of minuses here and a bunch of pluses here. And this is my depletion region. There? Okay. What happens if I hook the positive terminal of a battery to the P side and a negative to the N side?
It's,
Okay.
yeah.
Yeah, it's gonna push, right? So it's gonna want to have electrons going this way and holes kind of going that way, right? Which in order for holes to go that way, that means electrons are going that way, right? So this is trying to pull electrons out. And what do you have here? So you have a bunch of electrons. So it's going to want to force these electrons to jump in holes moving towards here. Because you just created bait for that, right? It's the voltage is going to be pulling them, however you want to think about that. So as they're not staying permanently there, they do have a random chance to jump to some other electron, but that random chance to jump back, and they're going to be stuck in that region. So unless you create a drift velocity, which is what, like a current, that's kind of going, it'll then carry them along and pull them. They'll know the net direction they want to go. So if they get that to jump somewhere else, there's going to be a pull in that direction, not an equal pull. So they're going to, if these start moving this way to be pulled out, simultaneously these electrons are flooding in. And where are they going to go? They're going to move over here to these holes. All right, so they're trying to move this way because there's a spot for them to go. Bump every. Truly, it's them move. They move, bumps along and moves. So it's not one that will just move, and it's not stable. But then overall looks like an electron. So it's kind of
So this is a diode. And diodes typically flow in one direction. So we get one direction. Why does it stop the opposite direction?
Okay. Right, so this one is what we call forward biasing. As you do this, the electrons come in and fill these pluses and these minuses go away. So what happens to the depletion zone? It shrinks, and if you get enough voltage, you're pumping on this thing, it completely disappears, at which point you got charge carriers all the way, and it works just like a conductor. Does that make sense? This is what we call forward bias. And it will resist you up to a certain voltage by this voltage differential formed in the depletion region. It's typically 0.7 because it's silicon. You would use germanium, it's going down, it'd be 0.3, right? There's all kinds of stuff, right? So, right, it's going to have a net voltage. If this voltage source is 0.7 bigger, I have removed that depletion region. What happens to voltage once it's past the depletion region? Charge carriers ready to go, they're in the right spot, everything's happy, hunky-do. I put a low voltage on it. What happens to an electron that's free when you put some voltage on it? It moves real quick. You got a whole bunch of them available here. So pretty quickly you start adding more and more, you get a huge flood. Because essentially there's very little resistance in this. So once you've gotten rid of that depletion region, which is the block, the valve that's turned off, you rapidly get a flow of electrons. So let's think about our diode in this, right? I mean, if I look at current versus voltage, right, I put a heavier voltage on this side, so we'll do that as the positive. As I do this, as I'm filling it up, you'll get a tiny current flow, right, as they're kind of filling in the holes. So less than whatever my 0.7 is or whatever, you get a little bit of a flow. Once I hit that 0.7, 0.3 or whatever your particular differential for that is, now all of a sudden, I get a huge amount. See how you just explained the first part of the IV characteristic? Cool, isn't it? It's a direct flow. Remember, we just started with, the Schrodinger wave equation, right? And, the fact that we can't have two different electrons in the same shell unless they have opposite spins. That's all we needed, and we literally ended up with this. That's what the IV characteristic of diabetes tells us. What happens if I flipped this now? All right, so we got this. Hopefully that makes sense. I'm going to have to go to sheet number 2. So we're going to have our P, and again, there's our halfway point, a bunch of minuses, a bunch of pluses. But now, I hook. All right, so let me just note this is forward. Please make sure you forward bias. The bias relates to the, I'm biasing it with this voltage source. Okay, so this is the opposite, so we're going to call it reverse bias. Okay, now what's happening to this? All right, and we want holes going this way, which means electrons going that way. All right, so these electrons coming in are flooding in. So they kind of just build up that depletion region.
Yes, it increases. This causes more resistance and
Because the voltage is trying to pull them this way, right?
yes.
So it's got to slam up against that, but they can't go with an insulator. So they create a thicker insulator. How about these holes going this way, which means electrons coming this way? Well, that's going to pull electrons out, which puts more of these in, and these electrons come this way. So it thickens that. So on both sides, it thickens the a little bit of flow to do this. So if we were to look at our IV characteristic chart, right, there is a little bit of flow in the negative voltage direction. Right, so we saw this one went kind of weak. On this one, there's a little bit this is those minority carriers increasing the thickness of this. And as you keep increasing the voltage, you'll thicken it and thicken it and thicken it. So you will get a little bit of carrier going, and that's why it's a little bit below. The minority carrier, so majority voltage, there's a little minority voltage that can go on here, but not much. What happens if I keep pumping voltage? Increase and increase and increase. Eventually it gets so strong, what happens? It blows something through that, literally. Right? It's going to get so bad this, right? Imagine I put like an aquarium ball. Maybe you've all seen aquariums that they have glass. Right? Imagine instead just like a little kid's aquarium, 10 gallons or something. What if you took that same exact glass, used it to build a 40-foot tall wall inside of a giant aquarium in a zoo or something? Those lovely walls this big. What's it's held on for?
They're gonna build up into
Sure. The pressure of the water gets so great, it's subs are amazingly. They get to a certain depth. Look, build them strong enough to go all the way to the bottom. You can build them stronger and they get a bigger and bigger. At a certain point, it's going to get so huge, wham, it breaks. What it destroys it. It will never work again. You have blown it up, but you will get a huge one. So if you see that one at the end, that's the avalanche region. You can design materials to get this earlier, but do not damage themselves in doing it. So there are some diodes that are meant to create this voltage region, and then you get a state breakdown. They still have the same shape, they just don't destroy themselves in the process. Yeah, so magic happens if it wasn't specially designed to do this. Right? Because meters have that function where they will have the second breakdown and it's not damaging. Right? So there are things like this that they take advantage of the avalanche region. And you can create clamp meters. In most of the things you're going to get, it burns up. When it burns up, it releases all that funny material, which gives you a horrid acrid smell because it's metal. Right? And we jokingly call it the magic smoke. Is everybody heard that kind of joking term, magic smoke?
Once the magic bulb comes out in the fall.
Yeah, that's how you know. The magic smoke is what made it work because once you smell the magic smoke and it's not in there, it no longer functions. This is a really stupidly old electrical engineering joke. It was an old joke when I went to school, if that gives you any idea. Right? But it is kind of one of those jokes that every ECE makes somewhere in their career, and it's kind of like an inside joke password, right? You know the joke, clearly you understand the idea. Okay, you're one of us. Right? So just know the joke. I mention it because it is almost a password, particularly with older engineers, but you'll be an older engineer sometime and you'll use it too. Right? Because they either get this or they don't get this. Right? But that's why we don't want to do it. And you get really good at smelling when you burn components and noticing where the hole is, because how do you find damaged devices in some complex thing? Looking for thermal distortions inside the outer casing lets you find out where somebody overheated it, letting the magic smoke out, meaning they damaged the material, which no longer has the properties. So this is the fun bit. Semiconductors, if you get impurities of the wrong type in there, remember what we said, once you get some of these they very rapidly put things in bad areas. That's too big, it just doesn't work. So it's got to be really, really pure, except for selective impurities we call dopants that enhance properties. On top of it, this is such a big deal. So I'm not just saying this for no reason. Let me just briefly go back to our lovely little chart. Right? When you consider this, right? We said 4 is our friend. We can do with 5. We can do with 3. Right? Almost everything else in this chart is just innately bad to be in the silicon matrix. It will screw up. It's no longer a semiconductor. So I've got to make sure it's not in the matrix, which means I can't use it when I'm manufacturing. Now we should start to see the danger that I'm saying. So then there's a question of what are safe materials to be used in the manufacture that are not going to damage this property. Well, as was mentioned earlier, noble gases, they are your friends. Anything in a noble gases, so it won't destroy anything. So those are safe. Gases can absolutely be used in manufacturing. You can also use hydrogen. Hydrogen ain't replacing anybody. It's no problem in this one. You can take ones obviously in this room and a few other ones, right? There are some ones that are just, it's the first couple ones, right, to the right and to the immediate left. So anything that we would use to build it with, these first few ones here, noble gases and that, any of those you can use. Which means you can use hydrochloric acid because it's one of those X's. So if you often see, we will process things with hydrochloric acid, those are okay. that beginning spot. In column 7, we can get one more. We should put a double X here because that's right. Those are good. We can do stuff with nitrogen. Right? We get those. So there's nitrous, right? Ones that go in. We can handle it, right? But you really just got those first few ones on manufacturing. So on top of all the other difficulties we have with material, you have to get stuff that's going to be good. Okay. So these are just some of our complexities. Just understand them. I'm not expecting you to build them, but you should be aware. Okay. That's where our challenge is. Unfortunately, some of these are very, very dangerous materials, which is why this is also hazardous and creates a pollution. Sorry, that's what you get for your electronics. Okay. Now, what can we do with this lovely diode? Now that we have, and we know that when we hook the battery for conventional current, it will flow in this direction. So we showed that forward bias, conventional currents. And unfortunately, that's the way people analyze their circuits. Conventional current flows that way. Right? But we showed in reverse bias, so this is forward bias, right? This direction is reverse bias, and we showed that does not work. Which means for reverse bias, it sees a wall. But if you forward bias it, you get a flow. That arrow works. Anybody recognize that one? There is your diode symbol. The diode symbol tells you P to N. Right? And just remember, it always flows P-N. Okay. Now, this bar right here, when you look at the device as a component, this bar is the one we usually do because it's noted as a blocker. So that's where you will see the band on your diode when you are looking at it. Okay, so now you know how to absolutely recognize, and you should remember what it is. That will also tell you this is the P material, and that's the N material. So you can have a look at any old diode, you follow the shop, and which way it works, and you the material is. And you can deduce it from its quantum properties. Yay! So let's build something with it. So let's take our lovely little diode. I'm just going to use the symbol, and I'm going to make A and B. So let's say I told you that the value of A was 1 volt. Can you tell me the value of B?
And the so
Sure.
yeah.
Okay, so 0.3 volts, right? Now, let me ask you, what if I told you that this voltage B was negative 70 volts? Would you believe me? Yeah, you're right. But why? Because from the voltage from the other side will just, it's even become stronger, water flow over, increase the voltage out on that side. What if I told you B's voltage was 1 volt? Would you believe me?
Just thirdly,
Not necessarily. What if we just actually told you it's 1 volt?
it's simple.
Could be right.
But you can't be right because there has to be something lost in the answer. Because there could be something.
Yeah, there could be pumps here. I could have a voltage source that supplies 1 volt on this side, right? In which case, this would be a volt. And this is how it's about. If I put a negative 7 volts to this side, this voltage will flow over and get this to 0.3. Okay? I'll just get a ridiculous amount of current. I might break the whole thing if I have to smoke. But if it's working is forbidding this to go below 0.3. Right? But you can have more of it. So that's as low as it can go. 0.3 is a minimum. Right? I could do something else that lets you go above it. There's no problem with it. I can make that 10 volts if I wanted to. That barrier in the other direction is just not going to change. It only flows one way. So this is a minimum. Does that make sense? So what if I told you in advance that B was 0.3 volts? What do you tell me?
Tell you that it,
Okay, so it could be. The other time it could be 1 volt, right? This is where we have to get into it, right? So we know 1 volt is a possibility, isn't it?
yes.
Right? If this was my fixed term, right? If this was my fixed term, we know that. If that's my fixed term, well, it could be 1 volt on A that caused this.
Yes.
Could it be 2 volts on A?
It could be.
If A is 2 volts,
It
here, what's that going to do?
it was
Very good. Look at this with 0.3. So is 2 volts.
it gets a standard, so yeah.
Could it be, yeah, so let's just take so. But could it be 0 volts over here?
Yeah. Yeah, because everything else is driving beer.
What if I have on this side something that's pumping 0.3, and I have something on this side hooking this to ground? Will the dynamic, like this is higher, so will it? So it just depends on the broken circuit.
Yeah.
So if I invert it, so could I put a grid on this side, and could I put 0.3 volts on this side? That's totally people, right? These people don't care about that. They're not doing it wrong. I don't care. I mean, usually the can go above 1. So 1 is the max. This becomes important when we do circuit analysis on this, right? So it's not just a single argument. People will be active and some will not be active. And you gotta realize, right? If this is below, it's just, it's just a break in the circuit. I mean, it's like if you cut the line, who cares? Right? On the end, you have to, and it goes the ranges, you have the currents flowing, and it's doing something.
A can be negative down.
One,
Yeah, I'm just thinking of the eventuality of maximum. So there was a point, there's a minimum that we don't know.
yeah, so there's a flip end, where if you go far enough, eventually that'll swing out and it's all done. Generally speaking, it's something 50 to 100 volts. So it's typically outside the range of most of your circuits when we design it, so hopefully you don't break them. Could you? Yeah, it's possible. But generally, we can worry about this one side because we're going to try to pick components that it, breaks areas outside. Does that make sense? Okay. So now you've got, so let me build 2 circuits for you. Here's my 2 circuits. All right. Let's deal with, I'm going to call these Roman numeral 1 and Roman numeral 2. Let's do Roman numeral 1. I different possibilities. I could have A and B. Now we're going to become very, very digital. 0 will mean 0 volts, and 1 will mean some large positive value bigger than whatever is necessary to bias this thing. Okay? 5 volts, whatever. Okay. These are all the possible combinations of A and B. We want to deduce what C could be, right? So let's start on the bottom. What if A and B were both 5 volts? What does that say about C? 4.3 volts. And between 0 and 5 volts, 4.3 is pretty close to 5. So we're going to call that 1. Make sense? So we know who this is. We're just going to say these are 5 volts when it's 1. So we know this is 4.3 volts. It's dropped a little, but it's still nice. How about here? A is 5 volts, B is 0 volts. So if A is 5 volts, what's going to happen with this? So this will be 4.3. This is 0, so this side has to be something bigger than minus zero point 0.7. And that says, oh, well, I want to make it 4.3, and this one says anything bigger than minus zero point 0.7 is okay with me. So what do they pick? They pick 4.3, so C is 4.3, so it's A. How about the other way around? Was A magic and B was just really. It's going to be the same thing to be one. What happens when they're both 0? It's not 0. When it's 0, we both say, we don't care if it could be anything bigger than minus zero point 0.7. But who's trying to make it be anything? Neither one's trying to make it anything. Right? Something bigger than minus zero point 0.7, but nobody's doing anything. Technically, this is what's called Z. The diode is off. That means we need to provide something on this side. What do you want it to be? You want it to be 0. I want it to be 0. So what gives me a 0? Well, you want it to be 0 just at a higher level. 0 is low. So you want to pull it down. Right? So you'll get the name immediately. I need a pull down. I want to add ground. But if I just added ground, when I get the high value, now 4.3 volt directed ground, what does that do? Really high current, we call that a short, magic smoke comes out, device will flip, and current happens. Right? So we need to put something to protect against too much current, which is a resistor. So we need a pull down resistor. Now, the second I do that, when it tries to go to 4.3 volts, this resistor will get a little bit of current flow off it, but it's not going to change things too much. And these ones stay the same, but this Z now becomes 0. So that's what a pull down resistor does. And you can see why it's called a pull down resistor. And we can talk in the future. How could I do a resistor? Well, you know this, it's 4.3 volts. You know this, it's 0 volt. This is a resistor. What relation connects the relative quantities here? And we said there's going to be some current flowing. We don't want so much current it breaks something. So whose law? We should medicate a bit. Whose law will help us here? Whose law, right? E equals IR, right? We know this. We have a limit of what we can tolerate. This, you go to your device and you can find out what can you pick less than. Right? So there's a safety margin. Calculate, find the resistance that will do that. Boom, you've got your R. Yay, you figured out how to calculate a pull down resistor. Right? If there's a whole bunch of things, add your current together. Pick a resistor that makes it safe for all. There you go. No problems. Good? What's this gate? It's an OR gate. Right? Real quick, the other way. Right? And if there are zeros here, right? Is anything happening? Right? How about if it's 0 and a 1? Well, if there's a 1 here, right? So if this is 0, what's the maximum that could happen? This could at most be 0.7, right? Yeah. So we know it can't, no matter what else you do, it's going to be down around 0. Could flow the other way from whatever circuit you're working on this, but it won't support more than 0.7. Otherwise it will flood. So I know that 0.7 is functionally a logical 0. How about in this case? A 0 and a 1. Well, if this is a 0, what can this be? So it's 0.7. If this is 1, it's 5 volts, so this is 5, maximum of 5.3, right? Maximum 0.7, maximum 5.3, or sorry, 5.7. What's it going to pick? No, maximum of 0.7 or maximum of 5.7. They both, this is the two required areas. What's the agreement region? 0.7. So that means this is a 0.7. How about this one? Doesn't matter which one was it. All right? 0.7. So these are zeros. What happens if they're both 5 volts? Right? But now we want to make sure, right, on this one, if they're both 5, I can see can be less than 5 here. Yes. And so this is that minimum side one. So this one can support either a 0 or 1, and it's going to depend on what you hook onto it. So it's B. Okay? And I need to supply to it now. So I need a pull resistor. So I need to pull on to get that one. Right? This one is the full gambit range. I need something to pull it out. So I put a resistor to limit it, and I hook it to the wall. You just did a pull-up resistor, and guess what you have the same exact stupid way. You find something, you know that your voltage range is on the other side. So maybe, and you find it when it's flowing, what's the voltage differential? How much current can these devices take in your day? Boom. You've now done pull up, pull down resistors, and this is called diode logic. I mean, what diode logic is, it's narrow. It lowers 0.43 on or 0.7 on one side, it raises 0.7. So you keep going stages, eventually you run out of differential. It's kind of annoying, but yay. All right. Next time we'll build transistor style logic. Any questions on these? Yeah.
So, how's the transistors?
I'll kick the dates back because we're a day behind.